Alright, we are recording. Hello everyone, this is Christian. I'm going to be going over an old exam 2 for Chemistry 1, General Chemistry 1, aka Chem 1311, specifically for the University of Houston, but if you're at a different college, this helps you out. I hope it does. Let's make this full screen. So, as you'll know, exam 2, we have same kind of tips as last time. Make sure you have your pen, your pencil, calculator. Make sure you know your username password. And same general tips for exam taking as the previous exam. Refer to the first 2 minutes of the previous video if you need help with that. There's also some general exam taking tips, on how to succeed in chemistry exams. So you might find that helpful as well. For this one, when I copied down the questions onto a Google Doc, as you can see, I've labeled some of them as MCQ. That means that there are multiple answer choices, but I have decided to just put MCQ because you can solve the answer without needing the multiple choices. Here you can see this one. You need to have the multiple different answer choices to figure out the question, so that's why I put that there. But we'll get to that when we cross that road. So question 1, predict the ideal bond angles in GeCl4 using the molecular shape given by Vesper's theory. Alright, so we know that Ge, using our periodic table, has 4 valence electrons. We know that Cl each has 7 valence electrons. So for our totals, we have 4 plus 4 times 7, and that gives us 28 plus 4, which is 32. So we have 32 total valence electrons between all the GAs and Cl. Oh, this should be a Cl4, by the way. So sorry. I forgot. When I copied and pasted them, some of them didn't copy the subscript, so I had to go back in and fix it, but I guess I missed some. But anyway, we got 32 valence electrons. So if we have Ge, let's make our Lewis structure, which is what I always recommend for these types of questions. By doing 4 bonds, we use up 8 of our electrons, so we have 24 valence electrons left. And let's just put it on our different CLs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Alright, so you can see we have 4 groups around the GE and no lone pairs among those groups. So if we were to draw out the 3D structure, it would be GE in the middle, right? You have a CL here, you have a CL here, you'd have like your solid here, and then your dashed somewhere here. And this gives you like a tetrahedral uh, molecular geometry and electron domain geometry. And for this specific structure, your bond angles will be 109.5 degrees. I shared in my workshop that there's a table for memorizing the bond angles and the molecular geometries and electron domain geometries. So make sure you guys know your molecular and electron domain geometries for the exam because those will be very important coming up soon. Alright, so next question is which of the following molecules is / are polar? So this is a multiple choice question, so you'll have multiple answer choices on like different combinations of these 4. So let's just draw these out, and I'll explain each of them after I draw them out. Again, I'm trying to make this video kind of similar to exam pace. It'll be a bit slower if I was to take this exam without having to explain all this stuff, I could probably go a bit faster, but I just wanted to be fair. Did I copy this down wrong too? No, this is CH3CHO. So this looks like this actually. Your CO2. I'm not gonna put lone pairs because I feel like that's just redundant. I think from exam 1, y'all should have known how to draw Lewis structures. So I'm gonna assume that you know that there would be lone pairs around these groups. I think it's more important that you see the groups that are on there, not just the uh, you know, not the individual lone pairs that are attached to everything. Look like this. You have your C2H6. So I drew some rough Lewis structures, and again, you can do this for this question if you're comfortable with making your Lewis structures. If you're not comfortable, uh, I would recommend you draw it out completely. They do give you electronegativity values for this question. However, I don't think we're going to need them, given you know your periodic trends and how, as you go up into the right of the periodic table, you have higher electronegativities and down into the left. And then you also need to know that C's and H's are roughly similar to each other. So that's another thing you need to know. So I'm gonna move this a bit so I can have more space. But what I'm gonna do here is I'm gonna draw out the structure of this, like the molecular domain geometries and whatnot. And what we're gonna do is we're gonna focus on this carbon right here. So what this looks like is you have a C here. I'm gonna put your O up here. You have an H here. And I'm gonna, if you're in a biology class, it's pretty common. But I'm gonna replace this entire thing with R, because we can see that, like I said, when C's and H's are really similar in electronegativities, um, they're going to pull on each other pretty similarly. So you know that there's not going to be a dipole moment uh, between these C's and H's. So they probably wouldn't be polar. So I'm going to replace this entire group with R. And again, this is common nomenclature or not nomenclature, but common like replacement for shortcutting things in biology classes. As you know, like for your amino acids, you have your R groups, which is what determines the identity. Like it's just a giant group, but anyway, before I start blabbering about biology, this is kind of the structure. As you can see, the shape it doesn't pull on the carbon equally, and we'll see that with CO2 as well. Like the opposite example of that, at least. And you can see that there's like a dipole moment here, right? Because we know that this oxygen is more electronegative. This one's more electronegative than the C's, the H's, and then this group is pretty much all the same. The R group is all the same electronegativities. So we know there's like a general dipole moment towards the oxygen. So if we're saying which ones are polar, I'm going to label this as polar. And here's the counterexample to that, which is CO2. So as you can see, for CO2, it would be a linear structure. So like if I just drew it like this, right? This would probably be what it looks like in 3D space. It's just a straight line. And the dipole moments would look like this. And as you can see, these oxygens are both equally pulling that carbon. So there's no net dipole moment. You determine polarity by net dipole moment. So even though these individual bonds are polar, the overall molecule is nonpolar. So I would say that this is not this does not have, this isn't a polar molecule. So I'm just gonna cancel that out. CH3Cl is quite a different case. So as we know, carbons and hydrogens have roughly the same negativities, but the Cl is, even the number that they gave us, you can see it's significantly more electronegative than C's and H's. So we know that in the 3D structure, if we look at this, if I draw it, it's a tetrahedral shape. Give me a second. Cl. And because it's tetrahedral, this Cl is gonna be more electronegative, so the dipole moment is gonna be towards it. And because it's not being equally pulled back by anything else, that's why how we determine this basically. So we're gonna say that CH3Cl is, it's polar, right? Because it has that dipole moment. As for C2H6, as I said, C's and H's are all, they have roughly the same electronegativity. Like CH4 we know is nonpolar. I think that was one of the examples for, like, your professor probably said that as an example when you're taking exam 1 or before exam 1. So CH4, we know that that's nonpolar, so C2H6 is just carbons and hydrogens. It's also nonpolar. So our answer for this would be CH3CHO and CH3Cl. And again, this is a multiple choice question, so there's multiple different combinations of these four, and it results in, these two being the answer. This is quite different. It is which of the following has a zero dipole moment? So, unfortunately, I think the best way to do this is to draw it out. So we'll just do just that. So NH3, and again, these questions do take a bit of time. I am so sorry about that. Like I said, I'm going to trust that y'all can do Lewis structures at this point. Y'all did it in exam 1. I'm assuming that y'all are pros at this. Your Lewis structure should look something like this. And I think like a good observation that you can make from this previous question is the structure has a lot to do with whether or not the molecule itself is polar. As you can see, this this trigonal planar one, because there's like an uneven, I guess, like direction, right? Uh, you can see that there's a dipole moment that does affect the polarity. Same with this tetrahedral structure. The shape did give way to there being a dipole moment across the entire molecule. But as you can see here in CO2, because it's linear, the dipole moments cancel each other out, which is why CO2 is overall nonpolar. So if we apply this to here, right? So if you draw your Lewis structure properly, you'll end up with this structure. And if we have nitrogen, we have hydrogen, hydrogen, hydrogen. As you can see, pretend that this lone pair group here is it's just basically pure electrons. And as we know, these are, if they had an electronegativity value, they'd probably be the highest out of anything, right? Because they're like I said, they're just pure electrons. So we know that there is a dipole moment here. So it does not have a zero dipole. So it has a non-zero, I guess, dipole moment is what you can say. For NO2, you get this structure. And again, I'm assuming that you know how to make Lewis structures. Uh, yes, it is an odd number of valence electrons. And you can see that the one way that you can think of this is kind of like this. Like you have your lone electron here, your one oxygen there, and your one oxygen there. As you can see, everything is uneven. Like I can't give you a definitive answer of where the dipole moment would go, but all that we need to know is it's uneven, basically. One of them has 2 electrons or 4 lone pairs. One of them has 6 lone pairs. One of them, the nitrogen, has a lone pair on itself. So in terms of the nitrogen, we can't really say where the dipole is going, but we know it's going to be non-zero because it's just uneven everywhere. Like if it was equal between 2 directions, then we can say okay, there's like let's pretend that it looked like this. It would be the same case as CO2, where they would go in the same direction. Unfortunately, it's not like that, so we know that there's going to be a dipole moment. And again, like I said, shape determines dipole moment a lot of times. If there's a case where there's uneven electronegativities, so NO2 is not. Next we have is PF5. Right? And for PF5, you should get a structure that looks something like this. And again, if we were to look at the 3D structure, it would look something like this, like that. Cannot draw to save my life. And I believe that this is called the trigonal bipyramidal. But as you can see, all these fluorines are pulling equally on that phosphorus. And so there will actually be a non-zero dipole moment because these have all been spread out evenly. They're all pulling on the P equally. There's no lone pairs on the P. So that's why the PF5 will be your non-zero dipole moment. And again, you can run through SO2 and HCN, and you will see that they also have you'll see that they have non-zero dipole moments, which is why PF5 is the answer. But I'm just gonna stop here just for the sake of time. As you can see, it's 12:03. You probably saw the date change. It's pretty late at night, so I'd like to go to bed as soon as possible. But yeah, that's why PF5 has a zero dipole moment. Again, when you're looking at these two questions, shape. Number one is there a difference in electronegativity? Number two is, does the shape contribute to the difference affecting the dipole moment? So just think about that for a second. What is the hybridization of the sulfur atom and sulfur tetrafluoride? Alright, so hybridization, as you know, whenever you put two atoms together, two elements together, they have, for example, like you have your one S2, two S2, two P6, etc., etc. Basically, sometimes you have to hybridize your various orbitals and subshells. So that's where this question is coming from. So if you do SF6, again, always start with your Lewis structure with these questions. You should know that there are 34 valence electrons total. Let me use a different color. I hate using red because I feel like red is a good way to, I don't know, correct yourself, which is what I did in this question. But I think I don't like using it too much. But SF6, we have 34 valence electrons. You draw your loose structure. The four bonds brings us down to 26 valence electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Alright. So now for hybridization, you want to count the amount of groups that are on this. So we have one, I'll use right here. So we have one group, we have two groups, we have three groups, four groups, and five groups. And based on the number of groups, that's how you label your hybridization things. So it's the same thing. You kind of go like SPDF. So we're gonna start with S. So we have let's do tally marks, right? So 1, 2, 3, 4, 5. So we have S, and S can go up to 1. I'm gonna erase one tally mark. We have P, and P can go up to 3 tally marks. So 1, 2, 3, 1, 2, 3, and we have a D, 1, right? And that's kind of how I do this kind of question, where you just kind of start taking off the amount of groups as you add them to your naming scheme, your hybridization scheme. And if we were to put this into numbers, it would be SP3D. Again, this is a multiple choice question, so you have multiple options to choose from, but SP3D is the correct answer. And again, this is just something you have to know. S usually goes up to 1, P goes up to 3, and D goes up to 5, I believe. But they typically won't make you go past the D. It'll usually like be SP3, and then maybe D1, D2 at most, for the exam at least. But that's kind of how you do it. You start with the group numbers. How many groups do you have around your sulfur, including your lone pairs? Those count as a group. And you start tallying them off. 5 groups total, 5 different things, I guess, 5 different exponents. So you get SP3D. This one is actually when I say FRQ, I mean like you have to type in an answer, so there's no like multiple choice. You can't just kind of guess on this. Again, I did that for the sake of time. Just copying and pasting is quite tiring, especially when you have to go back and fix all the mistakes when you do that. But BF3, right? Again, like I said, just draw your Lewis structures, simple stuff. 24 valence electrons, if you do that, F, F, and F, and then you get 18, you're down to 18, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and no lone pairs on the B. And like I said, your groups, 1, 2, 3 groups, so let's do 3 tally marks. You have your S can go up to 1, erase 1 tally mark. Your P can go up to 2, erase 2 tally marks. So you have, or your P can go up to 3, but we only had 2 left. Sorry, correction about that. So your final answer should be SP2. And remember that this 2 is an exponent. So whenever you're plugging in your answer, SP2, your 2 should be in the top. Alright, this is a multiple choice question. I put these are different answer choices. Let's just say this is A, B, C, D, and E. Alright, so I feel like this is more of a logic question. I'm not going to really read the first one, but, the first, like, as in this, use atomic orbitals combine most effectively to form molecular orbitals when, and I guess it's sort of more or less true or false thing. I'm getting tired. I am so sorry. I'm stuttering like crazy. But anyway, electrons in the orbitals have no spins. That is not true. As you know, when we draw our orbitals, let's say we have our pi 2p's, right? As you can see that one of them will have a spin, right? No matter what you put in there, they have spins. So we know it's not A. Electrons in the orbitals have the same spin, so these are our orbitals. And as you know, we have to fill them up singly and then doubly fill them up with opposite spin. So as you can see, each orbital, so if we look at just this orbital, they have different opposite spins, so we know it's not B. Atoms have an equal number of valence electrons. Not necessarily true. For instance, if we did like C and O, we can still do the the what's it called, the sigma 2s, sigma 2, sigma star 2s, pi 2s, pi 2p. We can still do that stuff even with CO or BO or BF, stuff like that. So it's not C. Combine most effectively to form molecular orbitals when atomic orbitals have similar energies. Um, this is actually true, yes, because if we um if we have similar energy, this is true in the sense that these two are similar in energy, right? Your two pi 2p orbitals are of similar energies, right? And your if we have our pi 2s, we know this is a different energy, right? Depends on the ordering of these, as you know in different questions. But overall, these two orbitals for the pi 2p have very close enough energies. So this is true. And only the orbitals are used in bonding. That's not true because we know we have our sigma 2s and sigma star 2s orbitals. So it's not E. Correct answer is B. Alright. Next. According to MO theory, how many unpaired electrons are present in B2? So you need to know how to draw your overall structure. So we know that 1b has 3 valence electrons, 1b has another 3. And the order for the B's are sigma, 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 pi, sigma, pi, sigma, I believe. No, it's one less sigma, right? It's sigma, sigma, pi, sigma, pi, sigma. That's kind of how you remember this. So this is your sigma 2s. I would label it just because your sigma star 2s, your pi 2p, your sigma 2p, your pi star 2p. Sorry, it's getting a bit small. And then your sigma star 2p. And as you know, one boron is going to contribute to one side, one boron is going to contribute to the other side. So we have 6 total electrons, right? So let's start filling them in, right? So 1, 2, 3, 4, 5, and 6. As you can see, there are your pi 2p orbitals each have a unpaired electron. So we have 2 unpaired. And one thing I want to keep in mind is, oh, whoops, right there. Oops. What the hell happened? Sorry. There we go. Whenever you're doing so this is the orbital diagram for all of the elements to the left of oxygen. For oxygen and fluorine, you should know that it's sigma, 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 pi, pi, sigma. This is just a side note. So this is your sigma 2s, sigma star. I'm just going to put a dot for the star 2s. Your pi 2, or your sigma, sorry, 2p, your pi 2p's, your pi star 2p's, and your sigma star 2p's. So for oxygen and fluorine, this is the case. And this is for, I believe, boron, carbon, and nitrogen. So just know that there's a difference between these two and know which one you have to apply when. Next is how many moles are there in 3.002 grams of ethanol. I believe we've had questions like this on the previous exam. Pretty simple stuff. Y'all should probably have a lot of practice with this, especially because a lot of questions do build on this kind of um, idea. So it's a lot of dimensional analysis, which I'm pretty sure y'all have had plenty of practice with. So 3.002 grams of ethanol. We know that the molar mass of ethanol, you add up 2 carbons, your 5, 6 hydrogens, and your 1 oxygen. Your molar mass is 46.087 grams of ethanol per 1 mole of ethanol. And again, you get this number by periodic table, getting your molar masses and stuff. You do that math, your units cancel out, you have moles, and you do that math, plug into your calculator, beep boop, beep boop. Your answer should be 0.0652 moles of ethanol. As you can see, it's a free response question, or I guess like a plug-in question, so you have to type in this number, 0.0652. Good question, but it'll build further questions will build on this idea. You'll see. 9. If the mass percent composition of a compound is 72.1% manganese and 27.9% oxygen, its empirical formula is blank. So, how you think of this is these add up to 100%, and you're going to say 100% equals 100 grams. You're going to pretend that you have 100 grams of uh, whatever, the combination of Mn and O, right? So how you do this is you have 72.1 grams of Mn and 72.9 grams, or 27.9 grams of oxygen. You're going to find the molar mass of Mn. Go to your periodic table. You should see it's 54.938 grams for 1 mole. For oxygen, you go 1 mole of oxygen is 15.999 grams of oxygen. Plug those in to your calculator, solve both of them, and you should get 1.312 moles of Mn and 1.744 moles of oxygen. So what this tells us is, if you had 100 grams of this compound, your formula for it would be Mn of 1.312 O 1.744. This number is not that fun to look at, so what we're going to do is we're going to reduce it to the lowest whole number by dividing both of these by 1.312 and this one by 1.312. Doing that, you'll get 1 mole of Mn, and you will get 1.33 moles of oxygen. So now your formula looks like this: Mn 1O 1.33. However, that 1.33 still looks kind of ugly. So what I would do is, if I were you, I would keep multiplying this. So multiply both of these by 2. So you'd have 2 Mn, 2.66 moles of oxygen. Still not pretty. You multiply by 3. You'll get 3 moles of Mn. And you'll have 4 moles, or 3.99, which is close enough to 4, of oxygen. And a question that I get a lot in my workshop is, well, if you have like this times 3, right, is 3.99, you can pretty much safely say that that is roughly equal to 4. If you get 4.01, you can say that's roughly equal to 4. So, again, your numbers won't be exact, most likely, but you should get close enough where you can make that rounding. If you get something like 3.67 for whatever reason, I would not do that. I would say, keep multiplying until you get a number really close. So your final formula is Mn3O4, and that would be your empirical formula. Looking good so far. And again, if you're watching this video while trying to do these questions, feel free to pause and do the questions before you hear my explanation for them. How many moles of C2H2 contain that molecules? So how you're going to do this is, we're going to start with this number actually, because that's what we're given. So 3.20 times 10 to the 24 molecules of C2H2, and it's asking for the amount of moles. So we're going to say that 1 mole of C2H2 is 6.02 times 10 to the 23 molecules of C2H2. And remember, molecules can, or moles can be 6.02 times 10 to the 23 of anything. You can have 1 mole of cars, that would be 6.02 times 10 to the 23 cars. You can have 1 mole of human beings, that would be 6.02 times 10 to the 23 human beings. You can have 1 mole of rocks, that is 6.02 times 10 to the 23 rocks. It's basically just a quantity, right? You do that, and you should get, let me see what my math says, 5.31 moles C2H3. So that's how many moles of C2H2 contain 3.02 times 10 to the 24 molecules. Now, this question is a bit more interesting. Oh, I forgot to fill this in. C2H2. How many moles of C2H2 contain 3.20 times 10 to the 24 atoms? So we know that, just remember, recap, right? C2H2 has 1 carbon, 1 carbon, 1 hydrogen, 1 hydrogen. So 2 carbons, 2 hydrogens, for a total of 4 atoms. So how we're going to do this dimensional analysis is, we have 3.20 times 10 to the 24 molecules, or atoms, sorry, times what we're going to say is 4 atoms is equal to 1 C2H2 molecule. And we know that 6.02 times 10 to 23 molecules is 1 mole. And the reason why we're converting from atoms to molecules is because it's saying how many moles of C2H2. So we do that math, plug it into your calculator, you should get 1.33 moles. I'm sorry, it's late at night. I'm just trying to stay awake. Cool. We're almost halfway there. When the following equation is balanced, what is the sum of the coefficients? There is a way to balance equations, which I will go to at the end. However, this one is pretty simple, so I'm going to show you all how I would do this if it looks pretty easy to solve. I would say that, we have 2 ALs here, and we only have 1 AL here. So I'm just going to say, what if we just give the other one 2? SO4 3 plus CaOH2 goes to 2AlOH3 plus CaSO4. Now, if you have your own method of balancing equations, I would stick to that, because I'm going to show you a more mathematical way of solving how to balance equations. I think a lot of y'all won't like it, and I'll repeat this. You can skip that section if you have a better way of doing it. However, the way that I do it, because I'm a bio major, but I have a math minor, so typically the math way kind of fits me better, but it might not fit you better. So, and again, I'll get into that later. But logically speaking, how I would think of this is I would say, okay, we have 2 ALs, we only have 1 AL here, bounce it out that way. The next thing I'm gonna do is I'm gonna put a 3 in front of the Ca. Reason for that is, or this right here, we're gonna put a 3 there. Reason for that is I'm gonna start balancing the oxygens, hydrogens, everything else, right? So as you can see here, we have 3 hydrogens here. Or wait, I think it was more in terms of the oxygens. Sorry, I'm getting really sleepy. But that's how I balanced it, at least when I ran through this earlier. So Al2SO4 plus Ca, or 3CaOH2 goes to 2AlOH3 plus CaSO4. Sorry, trying to stay awake. We do that. Again, I can't remember. Oh, I think it's the aluminum. My balance was the aluminums. That's why I did the 2 right there. Or did I? No, we did that step 1. For the for the 3, I'm trying to remember why I did that. I can't think of a reason. I'm pretty sure y'all can figure it out. I guess a challenge to the viewer, I guess. And to finish balancing it off, we're going to add a 3 at the end for the CAs. So Al2SO4 plus 3CaOH2 goes to 2AlOH3 plus 3CaSO4. And it's saying what is the sum of the coefficients when we balance it. So we've done this balancing work. So there's a 1 plus a 3 plus a 2 plus a 3. That sums up to 4, 6, 9. And again, don't forget there's a 1 here. So 9 should be your answer. Again, I can't, like I said, I worked this out earlier, and then I have a key that I'm running alongside. And I cannot for the life of me remember why I put a 3 in front of the CA first. So, like I said, make it a challenge to the viewer. See if y'all can figure it out. I'll let y'all worry about that. In a lab experiment, the reaction of that moles of H2 with that moles produced that moles of H2O, theoretical yield, and percent yield. So what we're going to do is we're going to first find our limiting reactant to determine how much of the H2O we can actually make, or theoretically make, So first is our theoretical yield. So I'm going to start with our 2.92, or let's make an equation first, sorry. H2 plus O2, according to this equation, yields H2O. As you can see, we have two oxygens here. This is pretty simple to balance. So we have a 2 here and a 2 here. And it should look balanced. Again, this is super simple. If you're having trouble with this, I'd say take a bit more time and look at how I was able to figure out that there's a 2 here and a 2 here. Alright. What we're going to do now is we're going to do our dimensional analysis to move from H2 to H2O and O2 to H2O. So 2.95 moles of H2 times, alright, so we have 1 mole, or we have 2 moles of H2, oops, my bad. Converts to 2 moles of H2O. We do that conversion real quick. We should get that we get 2.95 moles of H2O. Again, it's just 2. This is basically just multiplied by 1. Where it gets more interesting is with the O2. So we have 1.62 mole of O2 times, right? So we have 1 mole of O2 produces 2 moles of H2O. Do that math and we get 3.24 mole of H2O. So as you can see, our limiting reactant is the H2. So this is our theoretical yield in moles, right? So what we're going to do is we're going to convert this to grams. So 1 mole of H2O is equal to, what's the molar mass? 18.01, 0.04148. Do this, units cancel out, should get 53.14 grams. Is that right? Yes. So that is our theoretical yield of H2O. Alright. Give me just 1 second. Let me get my bearings real quick. I'm super tired. Oh, sorry, forgot the H2O. But that's your better answer for that. So we found our theoretical yield in grams. Now we're gonna find our percent yield. So let's call this part A. And then we get part B. Percent yield. So we produced 1.31 moles of H2O. So what we're gonna do is we're gonna use this number again. So we have 1.31 over 2.95. What this is saying is, out of our possible 2.95 moles, we produced 1.31 moles. We're going to times this by 100 to get a percent. You do that math, and you should get 44.4%. Again, you're saying out of 2.95 moles, you were able to produce 1.31. That's kind of how we determine percent yield. If you do chemistry lab, you've probably done this a couple of times, maybe. Or maybe that's more in Chem 2 lab. Not sure, but you're going to be dealing with percent yield a lot for this kind of question. Next question is, sulfur dioxide reacts with chlorine to produce thionyl chloride and dichlorine oxide. Give us an equation. If 0.4 moles of Cl2 reacts with excess SO2, how many moles of Cl2O are formed? Luckily, this equation looks balanced already, so we don't have to mess with that too much. Again, this is just simple dimensional analysis, right? So we have 0.4 mole of Cl2, and we have 2 moles Cl2. It reacts with excess SO2. How many moles of Cl2O? That's just 1 mole Cl2O. Again, you're basically just dividing by 2, so you get 0.2 moles of Cl2O. You should probably follow sig figs if they care, but that should be your answer. Quick question 13 was. 14, when 5 grams of ammonia react with, or 5.0 times 10, oh, I forgot to fix this. 5.0 times 10 to the 22, sorry, let me fix this. 4.0 times 10 to the 22 molecules of oxygen. How many grams of nitrogen gas are produced? They give us an equation. It looks like it is balanced already because they have a bunch of coefficients in front of it, and those don't seem random, so we're going to run with it. And the question is, how many grams of nitrogen gas are produced? So let's start with our NH3, ammonia. So 5.00 times 10 to the 22 molecules. Let's convert this to moles to make it easier on ourselves. 10 to the 23. What's 10 to the 23 molecules? I cannot write. And it is 1 mole of times 1 mole, or 4 moles of NH3. Yields. How much are we doing? We're converting it to how many grams of nitric gas? So 2 moles of N2. You do that math, you should get 0.0415 moles of N2. We're going to do the same thing for our oxygen. So 4.00 times 10 to the 22 molecules. 6.02 times 10 to the 23 molecules. 1 mole. We get 3 moles of O2. 2 moles of N2. We run that math, we should get 0.0443 moles of N2. So obviously this is going to be our limiting because we have less of it. So we're going to see how many grams we're going to produce with that. So 0.0415 moles, of N2 times 1 mole of N2. Molar mass of N2 is 28.0148 grams of N2. And we should get 1.16 grams of N2. So that's kind of how you solve this question. You first find out what your limiting is, then you determine from limiting to grams. I believe that this was on exam 1, right? I think. So, y'all should have a lot of practice with this. Which of the following substances would you expect to be a non-electrolyte in aqueous solution? So this is kind of goes back to, well, at least you can see here, this looks like some of your polyatomic ions, I think. So, sometimes you got to keep up with that. So here we go. H and Br. So electrolytes basically is when you add substances, right? So typically salts to water, they'll break apart, right? So for instance, the one that we all know is NaCl, right? When we put this in water, it'll be Na plus and Cl minus. So these are electrolytes because it kind of has to do with physics where they conduct electricity, basically. But HBr, right? You can produce H plus and Br minus. This one might look a bit trickier, but it's H plus and C2H3O2, which is minus, which is acetate. You should have known that for from your polyatomic ions. So you can see from these two examples, they're both forming some kind of ion here. So we know that this would be an electrolyte, which makes it not a non-electrolyte. So we know it's not those two. You have K plus and I minus. Those are also ions. Those are electrolytes, not non-electrolytes. CH3CH2OH. So this is an acetate because you can see that there's definitely more than 3 hydrogens in there. And so structures like these are all the bonds are basically non-polar covalent, or except for the OH part. But because none of the bonds in it are ionic, right? All of them are covalent bonds. We know that it's not going to break down in water as easily, and therefore it would be a non-electrolyte. So this would be our answer. And NH3, how you would think of this is it turns into NH4 plus and water. Because remember that we're in an aqueous solution, so some of these waters are going to give up its water to it, or this should be an OH minus. But a water molecule with NH3 would form that. Because remember, you're in an aqueous solution, so that's why that would form. And as you can see, this is ionic, or this is an ion, basically. That's why CH3CH2OH would be our answer. Alright, Next is question 16. When 0.102 moles of NH43PO4 is dissolved in enough water to make 1.5 liters of solution, what is the total concentration of all ions present in the solution? So again, like this previous question, we're going to break this down into its constituent ions. So NH43PO4 in water is going to form 3 NH4 pluses and 1 PO4, 3 minus. As you can see, these are 4 ions, basically. So we have 0.102 moles of this stuff. This is going to turn into 0.408 moles of ions. And again, we're just multiplying by 4 because we know that this breaks down into 4 ions. I have water on me? Yes, I do. My throat is getting dry. Alright. So if we're having 1.5 liters of solution and we're looking for the concentration, concentration is kind of they're kind of indicating that they want molarity here, which is moles of solute per liters of solution. And when you get to Gen Chem 2, you'll learn about molality, which is something completely different, but this is molarity, which is also capital M. So basically what you're going to do is you're going to divide your 0.408 moles of ions over 1.5 liters of solution. Do that quick math, you should get 0.29272, molarity. Again, simple math, you just do moles of solute over liters of solution to solve the concentration. Alright, we're almost done. Nitric acid is often stocked as a concentrated nitric acid, which is a concentration of 16 molarity. Common concentration used in the laboratory is 6 molarity of HNO3. If you need 20 liters of 6 molarity of HNO3, what volume of concentrated nitric acid must be diluted? This sounds really complicated, but remember we're looking for a volume, right? And basically what we're going to do is we're going to be diluting the concentration that we have been given. And our goal is to reduce it down to 6 molarity, right? So let's start with, we're needing 20 liters, right? So let's start with that. We have 20 liters that we need. We need 20 liters of this 6 molarity solution. So we're going to do 6 mole per 1 liter, right? The concentration that we have is 16 moles per liter. So to cancel our units, we're going to have 16 moles on the bottom and 1 liter on top. Again, what we're doing here is we're saying we have 20 liters of, we need 20 liters of something. We need 20 liters of this concentration of something, but we have this concentration. And so we need to figure out how many liters we need, right? So this liter and this liter cancels out, this mole and this mole cancels out, and our units are in liters. So we know we're kind of moving the right direction. We do this, and our answer should be 7.5 liters. And basically what we're saying is, if we get 7.5 liters of this nitric acid solution, we can dilute it from 7.5 liters to 20 liters, and we'll have the same concentration. So, I don't know. If you're misunderstanding this concept, I would say strongly suggest going back to your lecture slides and looking at it. But this is important. Yeah, drink the water again, sorry. Which of the following mixtures will all the compounds be soluble? This goes to our solubility rules. Something that I taught my students, which is a good shortcut, is it's called Cash and Gia. So let me draw it out real quick. Cash and Gia. And this is all soluble, and we have some exceptions. So cash and Gia, make sure you know this for your exam for sure. You have chlorates, acetates, sulfates, halogens, nitrates, and then group 1A. So these are all soluble, but there are some exceptions to them, most notably the sulfates and the halogens. So one way you can remember this is your exceptions to the sulfates will be CBS happy. And the last P and Y are kind of irrelevant. And for halogens, all you need is happy. So your exceptions to this is, so all these are soluble except for these. And where this comes in is, it's kind of easy to remember. It's CABASR, HGAGPB, and then HGAGPB. So what we're saying is, all these are soluble, but for sulfates and halogens, if a sulfate's with calcium, sulfates with barium, sulfates with strontium, sulfates are with any of these, it is not soluble. So, not soluble. If halogens are with Hg, Ag, or Pb, they are not soluble either. So we just kind of have to go through our list and find it out, right? So NaS, right? Na is a group 1A, so we know that that is soluble. Whoops, is there a check mark? AgCl4, Cl is a halogen, but it has Ag is right here, or so this is not soluble. So we can stop checking this list. Again, these are options like, let's say A, B, C, D, or E. So we're going to go on to B. Barium nitrate. So we can see nitrates are all soluble. We don't have to worry about it. So this is soluble. Ca is group 2, I believe. And carbonate is none of these. If it's not on this list, it is not soluble. So we don't have to worry about carbonates. KOH. K is a group 1A. That's soluble. Nitrates are all soluble. Cl is a chlorate and doesn't have any exceptions, so this would be our answer. And what I would do is I would check off the D and E as extra practice and make sure you know how they're soluble or not soluble. Again, cash and Gia, it is a good way to learn or memorize your solubility rules real quickly, and just know CBS happy and happy. Again, I found this on a website, by the way. If you just search up solubility rules, cash and Gia, it'll pop up. There's like some slides from some university somewhere, which is where I would check. All right, question 19. Which choice best represents a balanced net ionic equation for the reaction of aqueous H2SO4 with BaOH2? So, net ionic equation is basically just it's everything needed to make anything. So if you have you're kind of looking at your products. If your products are something aqueous, you don't have to worry about any of the things, right? So let's think. What's one of our soluble things here? So NaS, right? Let's use an example. So if we have Na or 2Na plus S, right, goes to what? NaS, Na2S, or S2 minus probably. Because this is aqueous, because it's soluble, is aqueous. If this was part of a bigger equation, we wouldn't have to write any of these for an anionic equation. Again, you're only looking at things that turn solid or things that turn liquid. So let's do that real quick. So we have H2SO4 plus BaOH2. And if you look at our cash and Gia solubility rules, we would know that sulfates, these have exceptions, but H2 is not one of them, or hydrogen is not one of them. So this is going to be aqueous. BaOH, barium is a which one is barium? I believe is barium group 2? No, it's not. But it says it's aqueous, so we don't have to worry about that. It's aqueous. We don't have any products, so we're going to have to determine the products, right? So we're going to put these two together and these two together. This is kind of how I do it. The outsides go together and the insides go together. So you have BaSO4. You have your H2Os as well, because H and OH turn into that, right? balance your equation, right? We know that we need two H2Os to fulfill this because we have two oxygens and we have one sulfate here. So that's kind of how you just have to make sure you balance the equation, right? And then remember that BaSO4, we're going to think about that. Is it within our solubility rules? Sulfates with a Ba is insoluble, so it's going to turn solid, and our H2O is a liquid. So all of these are going to be part of our net ionic equation because it's forming a solid or a liquid. So to do that, we're just going to turn basically all these into ions. So 2H plus SO4 2 minus. Again, you need to know your what's it called? Your polyatomic ions for this. Very important. Your Ba 2 plus. You're gonna have your two OH minuses. This is gonna yield your BaSO4 solid and your two H2O liquids. Again, you turn anything aqueous into ions, you leave solids and liquids alone. And this is your net ionic equation. Cool. We're almost there. Almost there. And finally go to bed, I guess. Small volume of a 0.1 molarity solution of HCl is required to neutralize the solution prepared by dissolving 10 grams of KOH in 250 milliliters of H2O. This doesn't seem as bad as it looks, right? Basically what we're going to do here is we're going to turn our KOHs, because we know molarity is moles per liter, we're going to turn our grams of KOH into moles and divide that by our liters of solution. So let's do that real quick, right? So 10 grams of KOH times 1 mole of KOH is molar mass, sorry, 56.1049 grams of KOH. You do that math, you get 0.178 moles of KOH. And again, you have to turn that into liters, I guess. Or we're trying to find the what's it called? What volume is basically. So what we're saying here is for this, right? We need to find the amount of volume of this that'll be 0.178 moles of HCl, if that kind of makes sense, right? Because you want to basically our goal is to react 0.178 moles of HCl with 0.178 moles of KOH. Goals to have equal amounts, right? So what we're gonna do here is we're gonna find out what volume we need, right? So 0.178 moles of HCl. We're gonna use our molarity here as our conversion factor. So we have 0.1 moles per 1 liter. You do that math real quick, and you'll see you need 1.78 liters. Again, what you're doing here is you're converting your grams of KOH into moles of KOH, and you're seeing, okay, we need this many moles of HCl, so we're going to use the molarity of our solution to turn that into liters. What is the oxidation number of chlorine in ClO4 minus? So for oxidation number, y'all should have learned this in class. It's kind of a lot to go into. But basically, you want to know that your oxygens are usually going to be a 2 minus oxidation number. So for ClO4, right, minus, this minus tells us that all of our oxidation numbers need to sum up to -1. So our, X, or blank CLs plus -2 times our 4 OHs, right? We only have one here, right? 1 CL. And our 4 OHs need to equal -1. 1, let's just put an X here. 1X minus 8 equals -1. And our X should equal 7 plus. So, or positive 7, but it's going to be, just put plus 7, right? That's going to be our oxidation number in chlorine. Again, it gets kind of mathematical. Recommend that you've, paid attention at least in algebra to do this question. Question below is balanced with the smallest set of coefficients. What is the coefficient of Zn? There is a way to balance this. You know, chemically with chemistry. Unfortunately, I'm actually more of a math person, so I'm gonna kind of show you all the trick to doing this. Uh, the correct answer is four. So if you know are solving this and you just want the answer is four. I'll come back to this afterwards, and I'll show you all the tricks to this. But the correct answer for the coefficient of Zn is four. Again, like I said, I have a really mathematical way of solving it that I'll show you all in the next step. Oh wait, is that it? Oh, I guess I forgot to put question 23. There's a 23rd question, but I'll just write it out for y'all because I forgot to put it in. Sorry. For question so please do this for me. For question 23, sorry. I forgot to copy this down, I guess. Bi 3 plus AQ plus Fe 3 plus AQ plus H2O liquid goes to BiO3 minus aqueous and plus Fe3 plus aqueous plus H plus aqueous. And here we're going to use half reaction. So one of my students asked me about this and I had not checked it out yet. I had not looked at half reactions much. So now I'm going to kind of go into it, I guess. So we're going to first determine our oxidation numbers, right? So for oxygen is, 2 minus, right? We know that our H has to be plus 1 plus, right? And there's two of them because it has to all sum up to 0. Uh, Again, this is determining oxidation numbers. Basically, you want all your oxidation numbers to sum up to the charge of the element or the molecule that you're looking at. Because oxygen is normally 2 minus, H has to be 1 plus each. BiO3 minus, so our oxygens are all minus 2. There's 3 of them. I'm going to do 2 minus. In order to find out what number this is, to get it all to a minus 1, we know that this has to be 5 plus. Fe is 3 plus, H is plus. Alright. Did I copy something wrong down? This should be Fe2 plus, my bad. So, let's start determining our oxidation numbers, right? Or our redox reactions. And to do that, we're going to use a mnemonic. It's called oil rig. Right, so oxidation is loss of electrons, and our reduction is gain of electrons. So basically, what we're saying is if something lost electrons, became more positive, it got oxidized. If it gained electrons, it was reduced. Right, so if it becomes more negative, it got reduced. You might get a question like this, like maybe a concept question. This person who took this exam did not get a concept question like this, so I would just make sure you know what oxidation and reduction is, because they might ask you like oxidizing agent or reducing agent, stuff like that. So just to be safe, make sure you know this stuff. Right. To determine our what got oxidized or reduced, we can see that Fe3 plus went to Fe2 plus. It became more negative, so we know that it got reduced, and it gained 1 electron. And then we know that our next one is Bi, bismuth. We can see it went from 3 plus to 5 plus. It got oxidized, and it lost 2 electrons. And so to do the half reactions, we're just going to focus on our Fe3 plus and our Fe2 plus, right? So Fe3 plus, so our first half reaction is Fe3 plus, Fe2 plus. Second half reaction is Bi3 plus to Bi5 BiO3 minus, right? Fe2 plus. Again, this is not that exciting. We know that we gained 1 electron, right? So to complete this reaction, I guess, you have Fe3 plus 1 electron goes to Fe2 plus. So that's our first half reaction down. Our next half reaction, we're going to go Bi3 plus goes to BiO3 minus. First thing we're going to do is we're going to balance this and for the first time ever, I guess, we can add stuff to this reaction. So we can only, the thing is though, we can only add waters, hydrogens, and electrons. So we only have oxygens here, so we're gonna add waters to our left side, if that kind of makes sense. So Bi 3 plus 3H2O goes to BiO3. Again, this is the process of doing your half reactions. You can see that we have 3 oxygens here. We need to have 3 oxygens on the left side, so we're going to do that. Now it's unbalanced because we have 6 hydrogens here and no hydrogens here. So we have to do this now. So let me just copy it down. And we have to have our 6 hydrogens, 6H plus. So by summing up our charges here, we have 6 positive charges, 1 negative charge. This is all 5 plus, and this is all 3 plus. So to balance that out, we have to add 2 electrons to the right side. So let's do that real quick. And we have to add 2 electrons. And so now this is balanced in terms of charge, right? Then now if we're looking at this reaction, right, we need to balance these two together. So as you can see, we have 2 electrons here, we have 1 electron here. So basically we need to double this this reaction. We just need to multiply that by 2. So we have 2 Fe plus 2 electrons goes to Fe2 plus. And now we should have our balanced reaction. We can just smush these two together. Everything on the left stays on the left, everything on the right stays on the right. Our 2 electrons cancel out. So we're left with Bi3 plus 3H2O plus 2 Fe. Was there an Fe charge on that? Fe3 plus, sorry, my bad. 2 Fe3 plus. Then goes to BiO3 minus plus 6H plus Fe2 plus. That's kind of how you balance this reaction. So the question was asking us, this question was asking what is the coefficient of water? Our coefficient of water is 3. So the answer is 3. Again, I forgot to copy down the question here, but just trust me, this is what the question was asking. So I'm going to go back to this question. Again, I kind of have to teach this. This is kind of again, this is kind of linear algebra. I took linear algebra because I'm a math minor. It is kind of fun to solve this way, but this is the way that I know how to solve it. Again, if you have your own way of solving this, you can completely disregard this part of the video. But I'm going to show y'all, I guess it's a longer but more guaranteed way of solving this question. So we're going to assign each of these values, right? So what we're going to do is this. We're going to say AZN plus BHNO3 yields CZNNO3 2 plus DNH4NO3 plus EH2O. And now we need to solve for A, B, C, D, and E. And each of these are in relation to their elements. So for zinc, solve for zinc, or what the coefficients for zinc would be, it would be A equals, right, we only have 1 here, A basically equals C, because we have 1 zinc here, 1 zinc here. This will start to make sense a bit later, trust. Next is our hydrogen. I'm just doing this in order of appearance. So for our hydrogen, we have 1 hydrogen here. So it's just B equals, in this part we don't have any hydrogens. In this part we have 4 hydrogens. So we need to do 4D. This part has 2 hydrogens, so this is 2E. I'm going to make this E look a bit more clear. And for our nitrogens, we have 1 nitrogen here, so we have B equals, for here we have 2 nitrogens. Again, this is completely optional. If you have a better way of solving this, you can do that. I'm just more of a math inclined person, so this is how I think of solving this. So 2C, or yeah, because we have 2 nitrogens here. We have 2 nitrogens here as well, so 2D. And last but not least, we have our oxygens. For ox, I'm going to do ox, so you don't confuse it with a 0. But we have 3 oxygens here, so 3B equals, we have 6 oxygens here, so 6C. We have 3 oxygens here, so 3D. And we have 1 oxygen here, so plus E. Now, if you can break down all these, so just give one of them a value and solve, like, I don't know, set E equal to 1 or something, You can solve for this. However, I'm gonna make it easier using linear algebra, basically. So a minus c equals 0, b minus 4d minus 2e equals 0, b minus 2c minus 2d equals 0, and 3b minus 6c minus 3d minus e equals 0. And again, I'd say if only learn how to do this if you've already studied a lot and you want to learn this stuff. This might take a while. You do need to learn about how to row reduce, which is you'll see that coming up shortly. But what I'm gonna do is I'm gonna make a matrix. So A, B, C, D, and E, and I'm just gonna plug in what the values are for each within these. So A is 1, C is -1, everything else is 0. Second equation, B is 1, D is -4, E is -2, everything else is 0. B is 1, C is -2, D is -2, everything else is 0. It's bigger. And then 3B, 6, -6C, -3, and -1. Alright, so now what I would recommend is you do is Google how to row reduce. You can do that. And I'm going to basically summarize that you can row reduce this. There are multiple steps to this, but this will row reduce down to 1, 1, 0, -1, 0, 0. This will be 0, 1, 0, -4, -2. Alright, it's bigger. This will be 0, 0, 1, -1, -1, and this will be 0, 0, 0, 3, -1. So again, if you have time for this, you can do this. If you have a method of doing this, that's better. You are wasting your time watching this part of the video. And then this gives us our final equations, which is a minus c equals 0, b minus 4d minus 2e equals 0, c minus d minus e equals 0, and 3d minus e equals 0. Some equations have changed, but this is still the same set of equations as each other. Again, this is linear algebra basically, but basically you can now solve for each individual equation. So I'm going to start from solving from the bottom equation and moving our way up. So I'm going to say A, or let's make a chart. A, B, C, D, and E, what they're equal to. I'm going to set E equal to 1. So what we're going to do is we're going to start solving from the bottom equation upwards. So 3D minus 1 equals 0. Or actually, I'm going to set D equal 1. That looks like it's easier. So I'm going to set 3 minus E equals 0. E equals 3. So we found our E value. Now we can move on to this equation. Oops, 3D. So we can do C minus our value for D is 1 minus E, which is 3, equals 0. And we know that our C equals 4. We can solve for B if we'd like. B minus 4D, each D is 1, so minus 4. Minus E, -6, equals 0. B equals 10. And A minus C, right? A is equal to C basically. A equals 4, so A equals 4. And for this one, again, that gives us our 4, which would be the answer. So that is that recording of how to solve a organic chemistry, or not organic chemistry, sorry. There was an OChem exam that was running today. You can see the mass migration from the library. I didn't take it. God bless, I did. I've already taken that class. But it took us about an hour and 13 minutes to take this exam. I believe that you get an hour and 15 minutes, so even with me yapping and doing all kinds of things, teaching you all how to do this, I was able to solve it. So this exam is definitely doable. However, I believe that on the previous exam, I was able to finish my work in 50-something minutes when I was doing exam 1. So this exam is definitely more time consuming. I would say definitely be more prepared. When I took Chem 1, this was the hardest exam that I took. This was the exam that I scored the lowest on, so, kind of just be prepared for some difficulty. But otherwise, I think I'm going to conclude my video there. Peace out. Have a good luck on your exams, and have a nice night. And I should go to bed soon. Peace out.